Hello, you fine internet folks. We are here at Supercomputing 2024 at the NextSilicon booth. And to introduce you guys to NextSilicon, since they have some upcoming announcements, we have...
Yeah, I'm Elad Raz. I'm the founder and CEO of NextSilicon. And I'm a software engineer. And, I'm really excited about the Maverick 2 product launch, our new chip. 5 nanometer, 108 billion transistors. And we are aiming for the Supercompute conference. We are now live from Atlanta, from the AC24, the biggest supercomputer show ever.
Oh yeah, huge this year. Over 17,000 attendees. It's massive. So talk a little bit about NextSilicon and sort of why did you pick HPC, since AI is all the rage today?
Absolutely. So we are next generation compute, starting with accelerated compute portion. And we have a unique architecture in the fact that it can run anything which is massively parallel. We decided to target the supercomputing industry because it's a huge market and underserved market. So supercomputing is a $50 billion market, out of which you have storage, interconnect, all the infrastructure. And when you just count the number of computing chips being sold, the CPUs, the GPUs, other accelerators, it's $20 billion a year. So it's a huge market that you can disrupt, and you have hundreds of AI-specific accelerators and GPUs. So I believe as someone who needs to raise hundreds of millions of dollars, it's better to show revenues first. And I think that the HPC is a big one. So we decided to start with the HPC industry.
Awesome. So talking about your new chip, the Maverick 2, sort of starting out and moving in, 2 100 gig Ethernet ports that we've been seeing headlines about 400 and soon 800 gig. 100 gig seems modest. Why is that?
So you need to understand how supercomputing works unrelated to AI and machine learning hardware chip. Because in AI chip, you have limited amount of fast memory, the HBM that are in the edges of the chip here, right? And the HBM has limited capacity. You can put like 2 terabytes of super fast memory on a single chip. Right now, the Maverick 2 has 192 gigabytes. There are some flavors that can reach up to 288 gigabytes, which is big. But for 350 billion parameters, for example, assuming FP16, right, you need a 700 gigabyte. So you can't put the entire weight on a single chip. You need a couple of them, and then they need all to communicate with each other and do reduction. So interconnect is super fast. My previous company got acquired by Mellanox. So I spent like a big chunk of my life doing interconnect for supercomputing, InfiniBand, Ethernet, RDMA over InfiniBand, RoCE, RDMA over converged Ethernet, and it's super hard. So the way that you need to think about the product is not that, hey, you're coming with a chip and an interconnect solution and everyone is going to use your interconnect, which is internet-based, and start doing RDMA on that. It's not going to happen. But what it's going to serve is financial sectors. So in financial sector, you have high-frequency trading, risk management, that the optimization point is latency rather than throughput. They don't need the 800 gig. What they need is to get a packet going to the processor core really fast and getting it out. So everything I said so far is how you can build a company in incremental steps. Okay, go to the HPC company, generate revenues, then move on to other verticals. And this is how we think about also with the interconnect.
Okay. And so speaking of interconnecting, feeding the chip, how much, I promise you I'm going somewhere with this. How much bandwidth do you see over the PCIe bus for this chip?
Right. PCIe is limited. Okay. PCIe Gen 5 16 lane is 64 gigabytes per second. It's like not nearly enough to feed data in and out.
Mm-hmm.
PCIe Gen 6, is going to be twice as that. And with 112 LR SerDes, that's like the speed gigabit per second. Yes, you can reach to 256 gigabyte per second with some overhead. Again, your Apple M1 has 500 gigabyte. Sorry, the M1 has 400 gigabyte, and now with the M4, it's bumped to 500 and something gigabyte per second.
550 approximately.
Yeah, so your laptop has more memory bandwidth than the PCIe.
Yes.
So the goal of accelerated compute is dividing the workload that some computation will happen on the host, localized with the host memory, and the majority of the time you want to stay on device, on chip, okay? So yes, obviously you want to put the latest and greatest, assuming support from the CPU side, CXL, PCIe. But our architecture is not bound by the PCIe because we have this smart algorithm that try to figure out what's important and place it on the chip. Now, once it's localized on the chip, you stay on the chip.
Okay. So speaking of the chip, so you have up to 6.4 terabytes of bandwidth from the HBMs into the chip. Well, yeah, absolutely insane. How exactly are you using all that bandwidth? So what exactly is that bandwidth accomplishing?
Sure. There were experiments on taking CPUs and adding, instead of DDR, putting an HBM. And users quickly realized that they cannot saturate the HBM bandwidth because if you think about it, assuming that CPU can every clock, issuing a load or a store command to the memory, and you vectorize everything and you get 512 bits, okay, maybe you can saturate the HBM, okay? And typically the CPUs are doing compute and you have misses, so it's like every 1 to 16 clocks, add 64, 96 cores working in parallel on the HBM. You can't feed them with the latest HBM, okay? And DDR more makes sense. Okay. We have a different architecture. It's not a processor core. It's hardware accelerator that can issue those wide chunk of memory and feed HBM. And we are seeing it now.
Okay. And so speaking of your architecture, moving in, sort of a yes or no question, is your SRAM distributed between all the different cores?
Yes.
Because that's what it looks like here. Is you have
those are the SRAM.
Okay. So if you have this SRAM and it's moving all this data around, because if I remember correctly, it's a spatial architecture. What is the NOC, so the network on chip? How much bandwidth does that have to do to move all this data around? Say if this core needs to access that memory channel.
Sure. So we call it, and excuse me for the language, the shit factor, because you don't want that one side of the core will communicate to the other side. You want to keep everything localized. And if you see here, those NOC barriers, those are actually barriers in between, and you get penalty crossing those tiles with each other. Okay? So there is a penalty, and the penalty is measured in latency rather than throughput. We design a NOC that you can have a full throughput, but even that, you don't want to walk around and roam around the entire chip. Now, most of specialized architecture run a domain-specific language, right? You need to write a ROCm for AMD or CUDA for NVIDIA, and the AI startup, each one has its own language, which is great. And one of the things that you can see in those accelerator is the way that memory works. The reason why you cannot use a C++ or a Fortran architecture is because it's not cache coherent. Okay, so inside the language there is a notion of a shared memory. That's the name in CUDA. Okay, in LLVM it's address space. Okay, address space number 3, which saying here is a localized memory. The processor core talk to that. If you want to go and access another one, you need to do a DMA and move data around. Okay, so obviously we have that feature because we can run CUDA and ROCm and other. But what happens if you run in C++ code? Okay, And the last thing about intelligent compute architecture is that you can optimize those features at runtime and localize the data so that each one of those data flow graph will communicate with each other and the data will stay localized. And yes, and if you have an address command once in a while that go to the other chip, you get the latency penalty, but it doesn't matter overall.
Okay. So now, as you were talking about programs and data, a sort of a known quantity with spatial architectures is trying to fit programs onto a chip. It historically has been very difficult because you never have enough SRAM to fit an entire program. How are you trying to get around not being able to fit an entire, so because program is data and you can't fit all of it and you work on data, how are you getting around this?
Yeah. So we have the notion of likely flow and unlikely flows. Okay. Likely flows are the computational kernels that happen most of the time. Those are loops. Loops aren't stored inside memory. They are not stored inside SRAM or the HBM. Those are not processor code. I don't have here instruction fetch unit and sophisticated branch prediction. There is no branch predictor whatsoever. There is a data flow, and I have limited. We don't want to go inside the inner of the architecture. So for now, we just keep it. I mean, imagine like an FPGA, but like FPGA for software, stereotype, something like that. And the way that it's work is, and the reconfiguration is changing the different ALUs beside each one of those computational graph. And then you etch inside the chip, like the function, the graph, and then you like fetch data in as data processing, and like every clock, new data coming in, new data coming out. So there is a notion in compiler called same program, multiple data.
Yep.
So you have exactly the same function. Well, SIMD.
Sorry. SPMD. Sorry.
And for example, there is no notion of vectorized instruction set. There is no very long instruction set because you can have many types on the data flow. I mean, it's just different, and it's like a mind fuck because you need to think about it in a different way. And it's rotating the computing architecture on the side and say, that is the right way to execute massively parallel application. And we were able to crack it down.
Awesome. And so our final question, or my final question, is what's your favorite type of cheese?
Well, I will start with the one that I hate the most, which is ricotta. My wife loves it, and one time she just gave me inside my mouth, and I couldn't. But I like most of stinky cheese, blue, Danish blue, for example, is my favorite one.
We just had another interview where Danish blue came up as their favorite. So thank you so much.
Thank you for having me.
Thank you for watching. Like and subscribe. I know I hate having to shill all that, but it does help. And hope you have a good one, folks.
Thank you very much.